A smart contract is a program that allows for financial transactions. Smart contracts are usually associated with the Ethereum platform, which has a language called Solidity that makes it easy to program smart contracts. Someday we will have smart contracts issuing insurance, processing legal claims, and executing accounting transactions. Smart contracts involve money, and they are likely to transact with cryptocurrencies. That makes them ripe targets for attackers. What are the vulnerabilities of smart contracts? What can we do to ensure the safety of a high-throughput, automated financial system? In today's episode, Haseeb Qureshi talks to Emin Gün Sirer, a professor at Cornell University, where he is the co-director of the Initiative for Cryptocurrencies and Contracts. Haseeb and Emin discuss how smart contracts work and how to secure them. Haseeb and Emin are both working full-time on cryptocurrencies, which makes for a detailed technical discussion. In our previous episode about the Dow Hack, Emin Gün Sirer was one of the protagonists of the story. You can find that episode as well as all of our old episodes by downloading the Software Engineering Daily app for iOS or for Android. We've also got several other episodes in the back catalog with Haseeb, one of my favorite guests to have on the show. With that, I hope you enjoy this episode. You are programming a new service for your users, or you are hacking on a side project. Whatever you're building, you need to send email. And for sending email, developers use SendGrid. SendGrid is the API for email, trusted by developers. Send transactional emails through the SendGrid API. Build marketing campaigns with a beautiful interface for crafting the perfect email. SendGrid is trusted by Uber, Airbnb, and Spotify, but anyone can start for free and send 40,000 emails in their first month. After the first month, you can send 100 emails per day for free. Just go to sendgrid.com/sedaily to get started. Your email is important. Make sure it gets delivered properly with SendGrid, a leading email platform. Get started with 40,000 emails your first month at sendgrid.com/sedaily. That's sendgrid.com/sedaily.
Emin Gün Sirer is an associate professor at Cornell University, where he's the co-director of the Initiative for Cryptocurrencies and Contracts. His research spans cryptocurrencies, networking, operating systems, and distributed systems. Professor Sirer is one of the foremost researchers and bloggers in the space of cryptocurrencies and smart contracts. Today, he'll be chatting with us about smart contract security. Gün, thanks for coming on the show with us.
Thank you very much for having me.
Cool. So, smart contract security, I want to start with the basics. So our listeners are going to be familiar with the concept of blockchains. We'll assume they're also familiar with Bitcoin. Describe for me what exactly is a smart contract.
A smart contract at its core is a program that can programmatically manage money flows or asset flows. So essentially, the way I think of this is for the longest time, we had programs that manipulated mostly pixels on the screen. That you type into them and they take input from you, or they take input from files, and they produce things that are either other files or perhaps an output for you to look at. And that's sort of was the dominant paradigm for computer programming for the first few decades of computing. And sure, we always had actuators and so forth and sensors as well. That was a smaller niche, especially the field of robotics has been taking off on that front. That's its own separate thing. But when it came to general purpose computing, literally the programs were limited to pixel manipulation and or bit manipulation. Now, with the advent of blockchains coupled into these programs, into smart contracts, you can actually have programs that programmatically direct assets, whether they're money or tokens that represent real-world objects, whatever they might be. They can direct those resources according to a preset algorithm. And you and I and other people can agree what that algorithm ought to be for all time. And then we carry through with the smart contract, knowing in full confidence that the program can only do those things that it has been programmed to do. And that's an amazing, amazing ability. It seems like a smallish thing, but it's not. because the entire notion of counterparty risk or trustee risk has been taken out of the equation. There is no fear that our agent, who's acting on our behalf, who we would normally have to tap into for directing money flows, is going to misbehave, because our agent is a program. It cannot misbehave. It can only do that which it has been programmed to do. So this, I think, is an amazing new idea. And if I look at sort of backwards at the history of mankind, if I look at what we've done overall in terms of organization, social organization, there are only a few things that stick out. And, starting with, savage living out in the woods, hunter-gatherer society, till now. If you think about the big events there, written laws, that really enabled a new level of civilization. Corporations that shielded their participants from personal liability, that opened up another wave of innovation. And if I think about sort of the gap between the East and the West, a lot of it is traceable not to actual technical things, but to social organizational advancements of this kind. And smart contracts I see as being one of these things that really open up a new set of possibilities.
Right. So to further motivate that, can you give me just some examples of maybe low-hanging fruit of things that, smart contracts entering into the normal world of commerce, what could they immediately solve or make much, much simpler?
Sure. There are many simple ones. The simplest one that, if I were to look at my news feed, just about every 2 weeks or so, I hear of some musician suing their agent because they did not get their share of the royalties. This, I think, is one of the simplest uses of a contract where of the money coming in, some percentage needs to go in one direction and another percentage needs to go into another direction. And the middleman there ends up, if you trust him or her with your money flows, and they can misbehave. And a smart contract can take out the unknowability, the unknownness of that person. So that's the easiest one, but we get into much more exciting ones with insurance, for example. If I think about an insurance company, it's really a peer-to-peer company, right? I pay into the system, so do you, and on occasion something bad happens to someone in some unpredictable fashion, and then the system ought to pay out. And the intermediaries in that system, they are not bringing the value. The value is coming in from the network of people. Well, if you could actually create the same kind of network, without the intermediaries, you could actually affect an enormous efficiency increase.
Excellent. So we're all here a technical audience, and we know that blockchains or public blockchains operate over a peer-to-peer network. So what exactly happens in this peer-to-peer network when a smart contract gets executed? Can you describe for me what all the computers in the network actually do? What's the consensus process?
Sure. So at its core, a smart contract platform like Ethereum, Tezos, and other contenders in that space, they execute a unified giant state machine. So that's a machine that takes steps in tandem. There are many, many replicas of it, and all the replicas take the same step at the same time step. So it's like the way they operate is we all decide, all of the machines decide that on the next sequence of steps to take. So they decide, for example, okay, Professor Sirer is playing chess and he's moving his pawn from e2 to e4 or something like that. And Haseeb is underwriting an insurance contract. He wants to put up, $100,000 and wants to insure somebody in Florida against frost, let's say. Let's suppose that you have some inside information on weather patterns this year. So these are the next few steps that the machines have to take. There is an initial consensus protocol. This is where a lot of the magic has to happen, where we all have to agree on the same sequence of actions that are to take place. And then we execute those sequence of actions according to their associated smart contract code. And as we do so, we update the state machine, and the state machine goes to its next step, whatever it may be. Then it essentially says things like, okay, well, Haseeb having underwritten this contract matches with this particular farmer or whoever else, and Professor Sirer having done e2, e4 is facing the opponent's move, etc.
So to put it simply, then, a smart contract is just a series of state transitions that all of these replicated state machines inside of a smart contract platform are executing in the same order.
Pretty much, yeah. A smart contract is a definition of it's a series of commands that you can execute, and their associated effects, right? So what are the acceptable moves you can make at any one time with regard to a particular arrangement? So in the chess game, for example, I only have so many moves, right? The rules of chess are encoded in the smart contract. In an insurance contract, you'll have a matching engine and so forth, and the conditions under which you match. So and then the underlying platform decides on what the inputs are from the users, sequences them using this process of consensus, and then executes them.
So Bitcoin, which most of our listeners will be familiar with, Bitcoin has very limited ability to perform some very basic contracts. Why is this? What is it about Bitcoin that has that property?
So Bitcoin, just by its philosophy, aims not to be everything to everyone. It aims to just do one thing, which is value transfer. And in fact, the developers in charge, the main developer group at the moment, is trying to take it away from a payments network and to make it a store of value network. So in some sense, Bitcoin has had its wings clipped. It has a scripting engine that used to allow people to do all sorts of exciting things and write different kinds of code at each transaction. But it doesn't have those features enabled at the moment. So what Bitcoin is good for is money transfers and value transfers. And Ethereum has a scripting language that was designed from the get-go to operate, to facilitate smart contracts. So the scripting language in Ethereum is Turing complete. You can express many more complicated things with it. It's also true that you could do similar things with Bitcoin using a whole lot of complicated constructs, but they become very cumbersome. So there are efforts to try to port smart contracts onto Bitcoin. So it's unfair to say Bitcoin doesn't support smart contracts. It could, but in the same sense that my car could be made to float if I worked really hard at it, right? It's just not designed for it. From the get-go, it's designed for a different function.
I think we can all see the enormous promise and the abilities that smart contracts would give us that we don't otherwise have. That said, smart contracts bring a whole host of security problems that are fundamentally different than most other security models. So describe for us what makes smart contract security so different from other kinds of traditional internet security.
Yeah, that's a great question. So we all know all of the illustrious ways in which smart contracts went south. There are so many that I think I was looking through a list just 2 nights ago, and I can't even remember all the different things and the amount of money that has been lost. It's easily in the hundreds of millions range. Let's see. So what makes it so difficult? A couple of things. One, it's a new domain. So with a different language that people are using at the moment. That language is untested, untried. It's a little quirky. So the programming language that people use to write smart contracts is one issue. The second issue is that the way these contracts are written has typically been that you issue the contract once and you don't get to change it again. People need that certainty from you. What that also means that any bugs you have are typically encased in stone. It's very difficult to undo any mistakes you make unless you have sort of thought about mechanisms ahead of time to compensate for unintended things that are happening in real time. So it's kind of like a moonshot, right? You build your smart contract up, you start trying to send it to the moon, and then it's hands off. You don't get to sort of, unlike regular software, you don't get to go up there and wrench it around when it's not functioning as expected. If Facebook has a glitch, you can be assured that there's a team of 25 people behind it trying to fix it in real time, and they just deploy the patch without even most people realizing that there was even a glitch. That you can't do that with a smart contract. It's once launched, it is what it is, and the only acceptable things you can do to it are those things that you with forethought placed into the contract in the first place.
Gotcha. So there have been some new kinds of security best practices that have been advocated for smart contracts. Things like upgradable contracts, short-circuiting, throttling. Can you kind of describe what these things are and what role they play in smart contract security?
Let's see. So quite a few things have been suggested. So a lot of these stem from essentially how do you detect when things are going in a direction that you don't think ought to be going, and what do you do in response? That's sort of the large space. I think the best example for this was the Dow Hack, which really gave birth to all of these responses. So I'm sure your audience knows the Dow Hack all too well, so I'm not going to go into the details. But I do remember the morning of the hack. And I remember waking up and, my Skype was going insane. The phone was buzzing like crazy. And there was a hacker issuing these transactions that were draining the DAO. And there was nothing we could do about it. And you could tell that something weird was happening. The balance was dropping. And yet, the thing wasn't really ready to make, to handle any proposals at the time when it shouldn't be dropping. So the balance should have been staying the same, and somehow it's just going down. And everyone felt powerless. So what do? There are a couple of things that people have suggested. So off the top of my head, people have suggested things like what we call multi-timed contracts. That is, you don't just have one contract, you create multiple contracts, and you run them in parallel. And money only comes out when 3 different versions all say the same thing. So this is a good way to inoculate yourself against bugs in the implementation. And the hope here is if you have 3 independent implementations, they would not all fail in the same way. And if you can uphold that, then you will detect when one of them is being exploited. And when that exploit is happening, you can say, hey, there is something funny going on with this particular implementation, but luckily the other 2 are keeping it in check. So this is not very different from the way we do high reliability systems. In spacecraft, talking about going to the moon, people will remember that the space shuttle had these 5 computers, right? And they worked as a sort of a series of voting computers. That every single action was replicated on all of them, and they would only do something if all of them agreed. Well, if a majority agreed, rather. So they would be able to tolerate some number of faults. So it's the same idea, except with code. So you write multiple implementations, and you try to essentially guard them with against each other. So this is a good idea. Except it, of course, might triple your costs of development. And also, you might not get the independence that you seek. If it's the same group of people writing the code, then the code will likely fail in the same fashion across all 3 of them. So that's one problem. Let's see. Another idea that has been floated is escape hatches. So escape hatches are a good idea for essentially... So the core concept in an escape hatch is this. When you detect that something is happening that should not be happening, then you bring your contract down into a more reptilian mode where it can't do anything fancy, and it just shuts down in essence and gets into some situation where only certain activities, say the owner kicking it back, for example, to function again, you can bring it back. So that's a good way to ensure that, for example, if we had the DAO again, it would most certainly have an escape hatch that says, if 2/3 of the people think something bad is going on, it should stop. Right? This was one of the things we suggested in the aftermath of the DAO. And that's a crowdsourced escape hatch, where if the crowd says something bad is happening, the contract stops functioning. So we were the first ones to propagate that idea. And I think it's a good one. Let's see. But there are other escape hatches possible. The trigger function in the escape hatch is going to be crucial, right? You don't want a trigger that can be triggered by anyone and everyone, because then the certainty of operation of the contract goes away. But you can have other escape hatches too. You can have throttling. That is so throttling is slightly different. So you can have triggers of the kind, if the contract balance goes down by this much over that amount of time, or if the desired correspondence between tokens outstanding and balance is lost. These are the kinds of invariants that typically will trigger an escape hatch. Then jump into a more restricted operation where people can't withdraw anymore, and hopefully the owner can figure out what's going wrong and kick it back into action. And then, of course, there's throttling, and throttling is the idea of the payouts being delayed and limited so that someone can't come in and empty out everything you've got and walk away with it. So if that is somehow managed over time, then you have an opportunity to monitor what's going on and perhaps intercept or freeze the throttled funds.
Every second your cloud servers are running, they are costing you money. Stop paying for idle cloud instances and VMs. Control the cost of your cloud with Park My Cloud. Park My Cloud automatically turns off cloud resources when you don't need them. Whether you're on AWS, Azure, or Google Cloud, it's easy to start saving money with Park My Cloud. You sign up for Park My Cloud, you connect to your cloud provider, and Park My Cloud gives you a dashboard of all your resources, including their costs. From the dashboard, you can automatically schedule when your different cloud instances get turned on or off, saving you 65% or more. Additionally, you can manage databases, auto-scaling groups, and you can set up logical groups of servers to turn off during nights and weekends when you don't need them. And you can see how much money you are saving. Go to parkmycloud.com/SEDaily to get $100 in free credit for Park My Cloud for SE Daily listeners. Park My Cloud is used by corporations like McDonald's, Capital One, and Fox, and it saves customers tens of thousands of dollars every month. Go to parkmycloud.com/SEDaily and cut the cost of your cloud today. That's parkmycloud.com/SEDaily.
Now, one big area of traditional security is protecting private or sensitive data. Normally, if you're not on a blockchain, you would just encrypt this data, you'd store it in some secure database with specialized access patterns. And now you described earlier the idea of like sort of a blockchain insurance company. Let's say that you were to have such a company on the blockchain. Most likely you'd have some sensitive or private data that you wouldn't want everyone to have. And of course, given that in a blockchain, everybody has access to the blockchain or the database, how on a blockchain would you mitigate information or privacy leakage?
Okay, so that's a very big question and a very difficult one. So if we're going to be honest about the limitations of this technology, this is one of its Achilles heels. That is, privacy is very hard to get on a blockchain. So there are various different techniques for hiding certain aspects of the data you might want to hide. So let's try to do this somewhat systematically. So let's see, if we're going to store something on the blockchain, the easiest way to make it not visible to other people is to encrypt it. That's trivial. But now what you've done is you're using the blockchain as just data storage, highly replicated data storage. And the problem that you had with privacy suddenly turned into a problem of key management. Now, who gets to have that decryption key? Under what circumstances? How do you pass it from one person to another? Those all become difficult. And since they now became, the key became an exogenous thing, it's outside the system, it's outside the blockchain, its management is harder to control, and rules about its management are not necessarily encoded on the blockchain unless you do you go to great lengths and involve some smarts. So there is that issue. The other thing one can do is store private data off-chain in some other system, accompanying system. And one of the core ideas here came from, say, Filecoin and other peer-to-peer storage systems like this. This takes the storage pressure off the blockchain. It still leaves behind the entire key management problem. There is, of course, the metadata issue. That is, so you and I can perhaps hide what we're doing, and perhaps you and I have shared some secret keys, and everything we leave on the blockchain is an encrypted blob form, so if anybody looks at it, they can't make sense of what's going on. But there's still metadata. The fact that we're interacting is on the blockchain itself. And if we want to hide that, then what techniques do we use? That's an open research question. There are some dumb techniques, like we just put up junk when we don't have anything to say to each other. But there are some smarter techniques for hiding metadata. So there's a big continuum of different kinds of techniques one can use. One of the most exciting things, of course, is zero knowledge proofs, where someone proves something to another person without revealing any information. Anyhow, so there are some exciting weapons in our arsenal, crypto weapons or crypto techniques in our arsenal, or dealing with this, but there is no easy solution. When it comes to private data and blockchains, I think it's the two are very hard to merge. And what I suspect will happen is that there will be new architectures that will emerge, wherein private data will have much stronger guarantees than what we have with both public and permissioned blockchains right now. So at the moment, we just have two kinds of blockchains, right? As everybody knows, we have the public kind, the Bitcoins, the Ethereums, etc. of the world. And we have the permission blockchains. where you, me, and everybody in a particular industry come together, and we designate some number of people as our record holders, and we trust them, and we trust those people to keep our data private. And maybe that's okay, but architecturally, I think these two options are not the only two options, and there are other ones that are about to emerge.
Can you go into more detail?
Sure, I can tell you a little bit about some of the work we've been doing at Cornell. So I see two, as I mentioned, I see two big families: the public blockchains, which are wonderful. They do a lot of things for us, but everything's out in the open. The permissioned blockchains, where once again we have a number of people and a designated set of record holders. I don't know that structure, that architecture makes sense. In a lot of industries, so it's definitely true that you don't want to have a single record holder. We don't want to just say Google should hold the world's records on healthcare. That's a terrible thing to do for a whole lot of reasons. But so that's bad. But the immediate reaction, the dumb thing to say to this is, okay, well, we'll just smear it across n different people, and it's going to require a threshold T of them to make any state transition, right? So I take my data and I store a copy at, I don't know, Deloitte Latouche, some other accounting firm, yet another accounting firm, etc. And, 5 of them or 50 of them, whatever the number might be. And then when it comes time to interact with this ensemble, I should interact with at least a majority, maybe a 2/3 majority of them, so that I can reconstitute the data. That's sort of the standard technique. This we have known how to do in distributed systems since the late 80s. So that's 30-year-old technology. We understand this well. From a business perspective, what have you done? Well, you still have a monopoly class, right? So you created, you took away, you were trying to avoid a monopoly. Well, you created an oligopoly. That ensemble, you still have to pay. They're not going to do this record keeping out of the kindness of their hearts. It's a lot of compliance work, a lot of legal liability. So you'll have to pay all of them. And now you're exposing to them your metadata as well. They know a lot about you, your frequency of interaction, who you interact with, and so forth. And in a post-Snowden world, it's actually quite dangerous, right? So these guys are going to be infiltrated the most and first. And if one of them is infiltrated, the data gets out, and suddenly your crucial business data is in the hands of people that aren't involved. In fact, you and I, when we are going into business, I think it's anathema to go and find another group of people and entrust them with our business relationship. I think that would not be my first reaction. If I'm going into business with you, I assume you're in good faith. You assume I'm in good faith. We just need some technology to help us keep the faith, if you will. We don't necessarily need to go out and find some other people and go through those mediators for all of our interactions. So at Cornell, we're working on some new technology for exactly this. The question here is, can you have a blockchain of one? Can you have a blockchain where only one node comes up and says, hey, I would like to hold your data for you, and I will do so with all the same guarantees, all the same immutability, integrity, auditability guarantees as what you're accustomed to from both public blockchains and permissioned blockchains. So that is without recourse to a third party.
Yeah, that sounds like a very fascinating work. How would you deal with the? So you might be able to use cryptography to ascertain that this person is actually, or this node is actually storing your data. How would you prevent for that data from getting destroyed or going offline or just disappearing?
You would make a lot of copies. And what you also have to do in the process is, as you make these copies, that you have to make sure that the associated security policies with that data are always enforced. Yeah, so that's an interesting direction. I'm trying not to sort of give away, the techniques too much.
Okay, sure. Well, we'll veer away from that so as not to reveal your hand.
Okay.
Yeah, no. So one thing that's true, I think, both in public and private blockchains is, one limitation of smart contracts generally is that it's impossible to pull any data that's not on a blockchain unless someone puts it on a blockchain. So blockchains can't make API calls. And so deciding on who reports on outside data and whether to trust what they're reporting is true is a hard problem. So what are the kind of solutions people have come up with for reporting off-chain data?
Yeah, so this is the Oracle problem. So if I can step back a minute, so let's try to identify what's going on, so the listeners can sort of put things in context. So what EVM gives us, what the smart contract platforms give us at the moment, is comparable to processors. It's like someone invented a replicated, trustworthy processor. And that's wonderful. It's as significant as somebody inventing the microprocessor in the 70s or something of that kind. But what has not yet been invented is the runtime for the programs that execute on that processor. So when I execute programs on top of a blockchain, I will want to necessarily interact with the rest of the world. And this typically means doing I/O. And I will want to import facts about the world. And on occasion, I might want to make calls out to other services outside. And so there are efforts underway to make all of these things happen. The technique for importing facts into the smart contract platform is known as oracles. And so the question is, can we build trustworthy oracles that can take facts from the outside, the external world, in some way or another, and import them into a blockchain? And so there's been quite a lot of work in this area. At IC3, my colleague Ari Jules has built a system called Towncrier. And the goal of Towncrier is to use secure hardware to act as a trusted intermediary that goes out and fetches data from trusted sources and gives you a certificate that says, well, according to Yahoo Finance, the price of GM is such and such. Let's see. So that's one way of importing facts into the system. There is another technique called shelling systems, where essentially a master student working with me built an early prototype of this, but we were unable to actually deploy it. We got shut down by Cornell's lawyers. But essentially what you do is you pose a question to the crowd, and you find out from the crowd what they think. For example, what was the weather like in Ithaca, New York on this fine day in October? And they will all say, oh, it's cloudy and warm. And so, and then you give them a small reward. And as long as they know that everybody else is going to be honest, it makes sense for them to all be honest. Anyway, there are some interesting game theoretic games to be played with shelling systems, but they are a wonderful and very exciting technique for importing facts from the crowd, for polling the crowd, if you will. And so the final technique, of course, is to try to keep the data that you need in the system in the first place. So as this entire industry matures, we're going to find that much of what we need is already there. For example, many contracts need an exchange rate for some token, right? They would like to take action based on the exchange rate. If we have decentralized exchanges, then you can just consult a sister contract that's also sitting on the same blockchain as you and get a reliable answer from that source. So we're slowly seeing the deployment of decentralized exchanges, and so we're taking steps towards this. And there are many other techniques, as I mentioned, for importing facts from the outside world.
Right. Now, one other difficulty that a lot of people have when writing smart contracts is that everything that happens in a smart contract must be deterministic, which is somewhat different than a normal computer. So, we talked about I/O as API calls, but another thing is just getting a good source of randomness is actually quite tricky on a blockchain. It's not obvious exactly how you do that. Can you kind of go into a little bit of detail, which might not be obvious to our listeners? Why is it that every operation that occurs on a blockchain must be deterministic, and what people have done to try to get randomness onto blockchains?
Well, let me try to explain why it's essential. So when you have all these replicated computers, it's essential that all of them agree on exactly what happened. If your machine decides that the state of a contract is Professor Sirer did E2, E4, like he advanced his pawn. Mm-hmm. Meanwhile, I somehow trick another machine into thinking that I moved with my bishop, then I could possibly explore every single possibility of moves and then try to pick the winning game at the end of the day. And so we cannot allow the state machines to diverge. If they diverge, we have what is known as a fork in the system, and it has terrible consequences in that the financial history of the world disagrees. Half your nodes believe that there was a move this way, or somebody owns $1, and half the other nodes believe that somebody else owns the same dollar, and that is something you can't have. The difficulty comes from trying to avoid this. So the entire state machine has to be deterministic. So you can't, for example, say, at this junction in time, at this instruction, pick a random number. If you did that, then your machine would pick, let's say, 17, and that's your number. My machine would pick 35, and suddenly different things would happen. For example, a lottery would pay out to person with the lucky number 17 in your case, and 35 in my case. Those are two separate people. And, if the guy number 17 tries to pay someone, does he have the coins? Well, not according to my node, he doesn't. So you can't just ask for a random number by saying, come up with a random number. You have to, in some globally coordinated fashion, come up with that random number. And protocols for doing so securely are incredibly hard to get right. So how do we come up with a random number? Well, we don't even know which nodes are part of the Ethereum network at any one time. It's a dynamic set. It changes all the time as people drop off the network, as they come into the network. So you can't really ask everybody. So you have to somehow get that random number from some source. The simplest thing that people have done in this space is they consult an oracle, a random number oracle. So you go out off of the blockchain and someone says, hey, the random number is 37. There are other tricks that people have used in certain contexts. So if you and I want to cooperatively discover a random number, what they do is you first pick a random number in your mind. You don't tell me. I pick 1, 2. And then you take the hash of that random number, you publish that. And I publish the hash of my random number. And then we reveal. This is a commit and reveal scheme. So now we reveal the two random numbers we had in our minds. And once I've committed the hash, I can't reveal anything other than the random number I had in my mind, because then it won't match its hash. So this is an okay scheme, except it suffers from a liveness problem. If you and I were wagering a bet, let's say you and I will, we bet $10,000 each, and you bet even, I bet odd, and then you commit to a number, I commit to a number, we're going to XOR those numbers. Well, if I see, so suppose you commit and reveal your number, and I look at this, and I've now seen your number, I now know the outcome. And if the outcome is not in my favor, then I could actually be a jerk and not reveal my number. And there I sit. And so in this particular example, you could maybe arrange the bet so that if I don't reveal it, this is a two-party example, if I don't reveal it, you punish me. That's okay. Mm-hmm. But there are many other instances where it's actually quite difficult to compensate for this immense power of the last revelation. So if you are doing a state lottery, for example, and some number of people are supposed to reveal their numbers, well, the last person to reveal his number, it knows a lot more than the others. So these commit reveal schemes are okay in some contexts, but there are many others where they just fail miserably, and so then you just go off chain, as I mentioned before. There are schemes for correctly picking random numbers, except they're complicated, and the first correct protocol for doing so came out about a year ago. So it took us a long time to get that protocol right. It's quite non-trivial.
Very complex procedure.
Correctness proof is also non-trivial. So that's why it took so long.
When your application is failing on a user's device, how do you find out about that failure? Raygun lets you see every problem in your software and how to fix it. Raygun brings together crash reporting, real user monitoring, user tracking, and deployment tracking. See every error and crash affecting your users right now. Monitor your deployments to make sure that a release is not impacting users in new, unexpected ways. And track your users through your application to identify the bad experiences that they are having. Go to softwareengineeringdaily.com/Raygun and get a free 14-day trial to try out Raygun and find the errors that are occurring in your applications today. Raygun is used by Microsoft, Slack, and Unity to monitor their customer-facing software. Go to softwareengineeringdaily.com/Raygun and try it out for yourself.
So we've gone into detail about a number of the security issues that one would face writing a correct smart contract. I've spoken with many software engineers about this, and a lot of people are very pessimistic that smart contracts can ever be written securely, given the difficulty of writing, even correct normal code. But writing correct code that natively transacts in money, and because it's on a blockchain, usually by its nature, transactions cannot be reversed. And it's also very hard to do insurance or risk mitigation on blockchains. And so many people just believe that this is kind of a fundamentally doomed project. What are your thoughts on this? Do you agree with this? Do you disagree with this?
I completely disagree with that final assessment. So I agree that writing non-buggy software is very difficult. It has always been difficult, right? We know from, I think, just experimentally or just looking at empirically what's happened. For every 1,000 lines of code, you see one fatal error, and maybe many more, right? And I've been lucky enough to call out quite a few of these ahead of time. So for the Dow, I think I was one of the co-authors on the call for a moratorium. We identified, I think in the end, 9 different flaws with it, one of which the hacker used. For Bancor, we called out the front-running problem as well as the rounding issues that they have. So we've been prescient, and indeed, it's very, very difficult to write non-buggy code. And in the same sense that it's very difficult to send a man to the moon, and it's very difficult to make a heavier-than object stay in the air. It's really tough, right? We spent like thousands of years on this earth without a heavier-than-air object up in the air, right? So kites were invented, I think, fairly late in the game, but let alone airplanes that carry people. That's just a very recent invention. So should we give up? But hell no. That's crazy talk. So what's there to do? Well, the science of finding bugs is advancing rapidly. There is much research to be done on formal methods, on verification, on languages for expressing smart contracts that necessarily yield a correct implementation, as well as many other things, as well as bug bounties, multi-timed implementations, escape hatches, and so forth, practical measures to make sure that, yes, there will be bugs, but we will manage to deal with them. Many of these things that people want to do can be adequately addressed with the technology we have even today. And so I'm not stressed out about this. Yes, there will always be bugs. We've always had buggy systems, and yet we managed to build systems that are robust in the face of bugs.
Right. So speaking then of buggy systems, the most popular language for smart contracts on Ethereum is Solidity, which is used to write the vast majority of Ethereum smart contracts. And after the Parity hack, which was a $32 million hack of a multi-sig wallet, Solidity and the EVM fell under loads of criticism for being poorly designed and having insecure defaults. You wrote about this in your own blog post covering the Parity hack. What are your thoughts about the design generally of Solidity, specifically as a programming language, and of the EVM as the underlying virtual machine?
Well, the EVM has been particularly resilient. I have not really said anything about the EVM. Solidity is an interesting case study. So the fundamental tension there is between having a language that looks familiar, that has good aesthetics, that is easy to use, versus a language that is easy to write secure code in. Okay, so secure code doesn't have to be at odds with easy to write, easy to understand code, but practically that seems to be the fundamental trade-off. And so there are those are the two things. Complicating this story is the fact that not only do you have to design the language, but you have to communicate its quirks to all of the practitioners. So there is a documentation and communication challenge with any new language to be used. So a lot of the bugs that we saw with Solidity were things that were well known, right? The reentrancy bug was well known. That's easy. The Parity missing private modifier, that's well known. There are many other things like this where we knew that a certain anti-pattern should never be encountered, but it wasn't communicated well enough. So what do I think about Solidity? I think it's actually a pretty darn good effort at finding a language that is easy to use. So I kind of like that language. I have a bunch of gripes about it, but at its core, the trade-offs they made are quite sensible. I like the aesthetics, I like the way it looks. And it managed to get into the game a whole lot of programmers who would have been put off if you suddenly said, well, before you write anything at all, you have to first take a course in logic, followed by a 6-month, crash course, follow-on course on program verification. I think that would have been a non-starter. So moving fast and breaking things is very much part of the credo here. It's going to happen. And you just have to have sort of a healthy attitude about these things where you say, look, this is kind of normal. And on occasion, there might be missteps. And in the early days, you can patch up for them in using some measures. And at some point, it's going to be, less and less easy. In fact, it's going to be way more difficult to compensate. So Solidity, in my view, is as I said, a decent trade-off. There is much to be improved in Solidity. I would like to see much better types. The type system is a little weird. People have to use the safe math. Floating point, or rather, fixed point is not supported well. So there are a bunch of other issues. The defaults are a little wonky. They should really default to internal and not visible to everybody else. So, but these are things that one can tweak, in future revisions. So I would not put the blame on the developers there. Like, this is not an easy thing to build. It's many dozens of people who work on it. Yeah, and there will be missteps. It's just part of the game. And the early adopters will see it, and they will have to cope with it. That's just normal.
Right. This might be an unfair follow-on question, but how, if it were up to you, how would an ideal smart contract programming language be designed?
That's an interesting question. One I've thought about a little bit, but this is far from my field. I'm a systems person. I do distributed systems.
Sure.
So I'm not a programming languages person. So I can give you the sort of the high-level properties. I would love to be able to understand invariants associated with the code up front. And I can't do that if the contract is just specified mechanistically. Maybe here's an anecdote. I think instead of being too abstract, let me tell you about what I see when I teach systems. I teach an operating systems course. It's typically the first time any of our students build something complicated. And they build concurrent systems that are supposed to be correct under all conditions. And so they give you a buggy implementation. And you flag it. We flag it. And out of 25 points, if it's buggy, you get 0 or 1. Okay, no more than that. If it's buggy, it's really harsh. So then, of course, you have the student immediately in your office, and you say, "Look, you did this wrong, and clearly or not clearly, I'm worried that this situation, something that shouldn't happen. 2 cars are colliding on top of your 1-lane bridge. This should not be happening." And then the student tells you, well, that can't happen because, for that to happen, this light has to go green, and that's guarded by this other thing, which is guarded by this thing. And for that to, you get this incredibly long reasoning for why that bad situation cannot arise. Now, keep your eyes peeled for this. Just about every single smart contract security proof is essentially a long litany of these kinds of I don't know what, these screeds or whatever the word is. So somebody just whining on and on about how the bad situation cannot arise. And altogether, it's just not convincing, right? I don't want to go through that logical process. What they're doing in that case, to be technical for your audience, is they're giving you a temporal logic proof. Right? They're saying that particular event or scenario cannot happen because it's guarded. Essentially, for it to happen, this has to happen beforehand, and the precondition will never happen. Well, I don't have enough life expectancy to potentially enumerate all of those scenarios. They're exponentially many in number, and rule them all out. The language has to rule them out for me. I want to be able to say, I'm worried about the following events. This is my invariant, and I want it protected at all times. For example, for the Dow, the number of tokens and the amount of money, it has to have a correspondence. It better ensure that for me, and if it's not doing that, there's something enormously broken. So that a good language would allow me to express that, and Solidity at the moment has something like it. It has these requires and so forth, but it's not exactly what I have in mind. So that's what I would really love to have. The other thing that's cool that I know about that most people haven't thought about is backwards reasoning. So I would love to see this in a language. So if any of your listeners are thinking about it. So in the 90s or in the late 80s, early 90s, when software safety was really big and people were building embedded systems, they came up with languages where you can execute backwards. So I would say something like, okay, I know one specific case, the BMW anti-lock braking system. Okay, there are some scenarios that should never happen. Can we start in that bad scenario and execute backwards and find out an initial scenario that can trigger it? So that's isn't that kind of cool? I think it's kind of neat. People also try to apply this to TCAS, which is the system that makes sure that the planes don't hit each other in the sky. So this is, I don't know if you ever heard it. I hope nobody ever did, but I'm sure someone will have heard this. Sometimes it actually blares out in a loud voice. It tells the pilots what to do. It says things like pull up, pull up. And in fact, it says it with like greater urgency. It says pull up, like it really shouts. And so, and if it's telling you to pull up, it should be telling the other guy to push down. And in some cases, it might change its mind because if the other guy is doing something counter to what he's being told. So in the TCAS system, you don't want a collision course. There were extensive studies of backwards execution trying to figure out for a given implementation, will it ever, what are the conditions under which it will tell, a bad thing to two pilots.
Interesting. And that backwards execution, it doesn't cause this sort of combinatorial explosion?
Sure, that's why it's hard. That's right.
Okay, gotcha.
But you need to couple it with a lot of techniques for trimming down the state space.
Right.
We, of course, on this topic, there are many other things we can do. There's symbolic execution, like this. There's an entire area of model checking that people have worked on, where they can sort of algebraically, not without having to explore every option, they can capture what would happen and then make faster progress through the state space of possibilities. Anyway, it's a fascinating area. So tools that help people, to help program designers, smart contract designers in this regard would be wonderful. Tools that are coupled well into the language or built into the language would be fantastic. So, I expect to see these for Solidity. I don't see Solidity's syntax or feature set as a debilitating thing. We don't have to scrap it and come up with something new, but we just have to evolve it towards a better foundation.
Right. That makes sense. So I want to shift gears a little bit. And so we talked kind of about the sort of abstract security properties of smart contracts, but I want to talk a little about what kind of security we see in practice out in the wild. So you spoke earlier about two of the biggest hacks in Ethereum history, which were the Dow Hack and the Parity hack. And famously, you presaged the Dow Hack and you wrote about the Parity one. How would you say the community has evolved in light of these attacks, and how has the average security hygiene or sophistication changed since then?
So the Dow Hack was monumental. Right. It really changed the way people approach the entire smart contract ICO space, in that people understood that it was difficult to write these smart contracts. You couldn't just sit down, go on a bender and write some JavaScript code and put it on the blockchain and have it retain some value. So what has changed since then? I think there's a much better understanding of the quirks of the Solidity language and some of the EVM runtime quirks. There's been a lot of effort spent on practical measures, as I mentioned, bug bounties, multi-timed implementations, and escape hatches. Just about every smart contract I looked at has had some kind of an escape hatch built into it, and that's been wonderful to see. I think it's irresponsible to build things without escape hatches. So that's what has changed. Has anything else changed at a higher level? I don't know. The design process, I don't know if that has changed. I think, are people writing qualitatively better smart contracts? Yes, they're better than they were at the time of the DAO. Are we secure? Are we there yet? No, by no means are we anywhere close. Are we going to see more exploits? Sure. Yeah, for sure. There will be many. It'll be a lot of fun.
All right, fair enough.
It will be. It'll be interesting. Yeah.
Are there anything in particular that you'd like to see be more adopted as security best practices?
Bug bounties would be wonderful to have. We should see more of them. There are lots and lots of smart people out there, and we're not tapping into their collective smarts as well as we should be. So let's see. What other best practices? There are tons of things that people are doing kind of weird. Not wrong, but weird. So again, I looked at the Bancor code recently, and they have their own math routines. That kind of stuff should be in the system. Nobody should be using safe math. Nobody should be using their own approximation of a log function or whatever else. These things should be provided, somebody should do them correctly and once and for all. And we should never, ever have to audit that kind of code again. So Bancor had all these magic numbers smeared all over the place, and it turned out that some of them were slightly incorrect. So, yeah, this is best practice-wise. The more is in the system, the better it is. And so the more somebody spends effort to get it right once and for all and build it into the runtime, into the language, the better off we all are.
Right. Makes sense. Now, I suspect that, so kind of zooming out a little bit, one fundamental limiting factor for the wide adoption and usage of cryptocurrencies is the difficulty of key management. And a lot of people believe that most normal people will just never be able to do this well enough to be able to use cryptocurrencies realistically. How do you see key management as a security problem evolving?
So that's that pessimistic stance is what we started out with when we were first looking at Bitcoin, right? So I'm sure everybody knows this, but Bitcoin thefts are happening all the time. People lose their keys constantly. And there is no shortage of messages on bulletin boards saying, hey, I lost so much money, I lost so much other money. And then, there's the litany of responses, which is sorry for your loss. And then it gets repeated so many times that it has gotten contracted down to SFYL. So an SFYL event is like a thing that we talk about. So what happened? I had an SFYL event, right? A sorry for your loss event. So, where is this stemming from? It's stemming from the fact that for many years, the developers essentially outsourced the security task to other developers. So instead of securing the cryptocurrency using the cryptocurrency system, it didn't occur to them that they could take on that task. They always thought, well, if your phone is hacked, it's your fault. So what does that, or if your laptop is hacked, it's your fault. Well, it kind of might be. I mean, it is a fault for sure. But if you begin to say that, if that's your mentality, then what you're really saying is these systems will always be beholden to the security of the underlying computational platforms, our phones, our laptops, and those things are nowhere near secure enough for high-value assets like crypto. So your regular old Verizon branded Android phone is way out of date in terms of security patches. So if you're using one of those and you're holding coins, you will get hacked. You're going to install a stupid flashlight application. It's going to ask for every permission on earth, and you want that light, so you'll say yes. And then the next thing you know, it's sending your coins to whoever, someone. So this is just the way of it was the way of crypto, and it seemed really hopeless. But Itai Eyal and myself, Itai Eyal is now a professor at the Technion. He was a postdoc at Cornell. Itai Eyal and myself, we took a look at this whole situation and we said, look, it doesn't need to be this bad. We can protect some of these coins and we can invent mechanisms that are actually helpful in stemming attacks of this kind. So the simplest thing that we came up with was called covenants and vaults. A vault is a mechanism for protecting your coins that are not in motion. When you are not going to use your coins, you put them in a vault. If the hacker breaks in and moves your coins, then you get to undo the hack. To pay someone, you have to unvault your coins. You can't just pay out of a vault. So the finality of Bitcoin transactions is not affected. And yet, if somebody steals your coins, you get them back from the hacker. This is a pretty cool feature. Anyhow, so there are actual advances that help the state of the world. Of course, the Bitcoin world is so busy with the ongoing craziness with the block size debate that they haven't had time to do anything except a very convoluted, complicated hack called SegWit. So they haven't adopted this yet, but we've seen adoption in other areas, in other systems. But there are things we can do, and I would urge the developer community to start looking into actual in-crypto mechanisms for better security. Do not rely on the Android developers to give you a perfect operating system. That is never going to happen. Do not expect a laptop to be uncompromisable. Never going to happen. It's 50 million lines of code in there. Of course there will be flaws and bugs and so forth. And plus more that users actually install. Mm-hmm. So don't wait for those platforms. It's not going to happen that way. You're going to have to build in features to protect your users.
Gotcha. So Let's kind of again shift gears one more time and kind of look toward the future of blockchains. This is something that you write quite a lot about. Interest in blockchains and cryptocurrencies have hit a fever pitch, and it's to the point now where a lot of massive companies and regulators are starting to whet their appetite and want to get in for a piece. Are there any key events that you're looking for on the horizon that you think are going to be major inflection points in the future of blockchains?
Sure. Regulation of the exchanges. At the moment, there are a large number of exchanges that are running wild. They have, they operate out of funny jurisdictions. Nobody knows exactly where they are, what laws they are subject to. Nobody knows their internal state. And there are lots of indications that they might be doing something funny. When we see the regulators move in and start trimming that kind of behavior, start intervening in exchanges gone wild, then we will see a shift. The money that is currently on the sidelines, it comes in only to the extent that the holders are greedy. They look at what's happening. They're like, hey, I want a piece of this action, and I'll take the enormous risk of being bamboozled at an exchange. So that there is some money of that kind, the greed, the sort of the risk happy greedy people. But there is a lot more money on the sidelines, orders of magnitude more, in the hands of people who are looking at this saying, this is a legitimate area. All of the sort of the geeky crowd is saying this is really exciting. There has to be something here, except the risks are too much. The markets are too unregulated. In fact, the SEC pronouncement had everything to do with just how terrible the exchanges were, and how.
Sorry, can you go into detail? What was that SEC announcement, real briefly?
When the SEC ended up clamping down on the Winklevi's ETF, proposed ETF, they said that an ETF at this point in time would be a bad idea because the exchanges are unregulated and there are all sorts of shenanigans that people pull at the exchanges, such that exposing your regular retail investors to the kinds of exchanges that currently run the space would be a folly. That was their reasoning. And it's, you can argue all you like about SEC. Nobody likes regulators, right? Nobody wants them to come in, etc. And you can say, well, the system is going to self-regulate and so forth. And I definitely am not a fan of hard regulation. But if you ask me what is the next milestone on the regulation front, them stepping in to curb the excess, the crazy shenanigans at the exchanges is going to be the next big step. It will drive away some of the money, and some of the illicit flows might go elsewhere, and I'm perfectly okay with that. And it will bring in, if done right, it will bring in a lot more money that's sitting on the sidelines.
Right. That makes sense.
And there's much more clean money in the world than there is, illicit flows.
True. Very true. Now, in your blog, as you're writing a lot about cryptocurrencies, you say that your mission in your blog is to be a bulwark against the rampant misinformation and foggy thinking in the world. Now, cryptocurrencies have had a massive influx of attention in the last year, and a lot of new people entering into the cryptocurrency community, most of whom are less informed and less technical. Maybe they care more about trading and speculating than they care about technology. Do you think this has... let me ask a two-pronged question. The first is that how do you think this changes the culture and the progress of cryptocurrencies? And also, do you think it changes the prospects for its success?
Yes, both in a very positive direction. So the new people coming in, they don't have the baggage of the old timers, and they come in with an open mind. They typically come in because they see something exciting, or they see the opportunity for making money, and both are fine. That crowd typically comes in with a more open mind than somebody who has been a Bitcoin into Bitcoin since 2011. Okay, so what I see as a big problem in these systems, at their heart, they're open source projects with a user community, and they're valuable to the extent of their user community. Right, so the sum total of wealth inside Bitcoin is capped by the amount of money people have put into it. It's capped by the number of people who are excited about Bitcoin. New people coming in with a fresh viewpoint is always good. New people coming in, building new services on top is a wonderful thing to have. And that will displace the toxic situations that we sometimes see in communities. Maximalism is always a bad thing to have. infighting is always a bad thing. And no matter what side of the block size debate somebody might be on, big or small blocker, nobody's happy about the block size debate. It's just nothing, it's just no joy. It's just not good. And cutting that down is always good. And the best way to cut it down is to bring in a whole bunch of people who are going to say, guys, let's just find the block size and move on, because there's so much more to do on top. That's, I think, exciting.
Right. Well, that's really great to hear that kind of optimism for you. I'll have to take that with me. So that I think we've come up on the end of time, but I wanted to thank you so much, Gün, for taking the time to chat with us. It's been a fascinating conversation.
Thank you so much for having me. It was indeed a lot of fun.
Thanks to Symphono for sponsoring Software Engineering Daily. Symphono is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symphono.com/SEDaily. That's symphono.com/SEDaily. Thanks to Symphono for being a sponsor of Software Engineering Daily for almost a year now. Your continued support allows us to deliver content to the listeners on a regular basis.
Wow!